Today we're going to learn a lot about circuits. And circuits are important in our lives. We use them every time we turn the lights on or every time we pick up our cell phone and we go to check our messages. We use them every day to make our lives more convenient, to do more powerful things than we could do without them. And it's hard to imagine any part of your life that's not touched in some way by electricity and by circuits that carry that electricity into our homes and into our lives. Now, a circuit is simply a pathway that allows electrical charge to flow. Remember, we said the other day that there are, these electrons that are on the outside of the atom, outside of the nucleus, and they have this negative charge to them. And because many of those electrons, the further away they get from that nucleus, the more likely they are to kind of maybe just fly away or slip away, or it becomes easy for a passing atom or molecule to just kind of pull that electron off. And in certain cases, we can actually kind of push the electrons on the atoms in a substance to kind of just move and switch atoms and switch molecules and flow. And it is that flow of that negative electrical charge from those moving atoms that causes sort of like the magic to happen inside the circuit and causes the lights to come on or the computer to work, your cell phone to function. Now, there are two basic types of circuits that we use every day. The first kind is what we might call a power circuit, and this is where we get our power from in our homes, in businesses. When you turn the light switch on the wall, your power, your lights are coming from a very large electrical power grid that has lines that cross states in some cases and carry that electrical charge through your home's wiring system and back. Typically, there's a big generator or a series of generators at one end of a power circuit, and we're not going to really talk too much about what generators are, but that's something that you could look up if you wanted to, or we could talk about individually. And also, a lot of objects along that big circuit that are pulling power and using it to do things like lights and household appliances like refrigerators and washers and dryers and things like that, air conditioning units, heating units. In between the generator and all of those appliances and lights, there's a whole bunch of lines. There's these things called transformers. We generally hear about those when they blow and your lights go out for a couple hours. Well, the electric company comes out and fixes that. And something called circuit breakers. If you've ever had to go to the circuit breaker box and throw a breaker, then you've kind of heard of those. By the way, that weird sound you're hearing in the background, that's my dog. He's making horrible sounds, and I really hope you cannot hear them. Okay, the second kind of circuit is an electronic circuit, and these tend to be much smaller. These are circuits that are built and usually contained within our objects in our homes, like our computers, our cell phones, our televisions, radios, any electronics that you're using, your video game consoles, your remote controls, all that stuff. Now, it's not just a matter of scale, but the matter of scale is there for sure. Now, let's start to think a little bit about what is actually required to make a circuit. Now, you need three things in order to have a circuit that works. The first thing you're going to need is an energy supply. The second thing is a closed conducting path. And the third thing is what we call a load. Let's talk about each of those one by one. First of all, if you want to have a circuit that works, that does something, then you have to have some source of energy, or sometimes we call this a power source. This energy, it's electrical energy, and it is what pushes the electrons through the wire, let's say, in your circuit. you need something that makes sort of this pressure or this force that pushes on the electrons. Otherwise, the electrons are just going to sit there. And we call that force or that pressure that pushes the electrons through the circuit voltage. We measure voltage in volts, and it's a capital V for the symbol for volts. We'll come back to all of that. And an energy supply, all it really is it's a source of that push or that pressure, that force, and therefore it's a source of voltage. Examples in our daily lives would be like batteries or a generator, a power, sometimes they're just called power supplies, or a cell, power cell. Now, once you have an energy supply, you need something to carry the electrons in the circuit. So you need some kind of pathway. Often this is a wire, although when you get into electronics, there's conducting paint, and there's really some cool stuff out there. But for our purposes, we're going to think of wires as being what makes up the pathway in our circuits. And you need that pathway to be closed. We'll look at more of what that means in a little bit here. And you need it to be a conducting pathway. Now, remember when we talked about atoms, we said that atoms have a nucleus that's positively charged because of the protons inside of it. And atoms have electrons, negatively charged particles on the outside. And remember that in some atoms, those electrons are kind of held closely to the nucleus. They're kind of held tight. And it's very hard for those electrons to fly off or to get pulled off by some sort of push or pull or a passing atom or something like that. But remember that other atoms, they had electrons that were kind of far away from the nucleus. And there's some other factors involved too, but you can think of them as kind of being loose and far away, and it's easy for them to just fly off at the smallest thing. And so if you give them a little push, they're just going to pop off that atom, and they're just going to go hitch on to the next atom, and they're just going to kind of move through the material. We call those atoms that have loose electrons that can easily move from atom to atom conductors. And most metals are really good conductors, and most metals have a lot of atoms that are just kind of, in there with their electrons moving all over the place and flowing if there's an energy supply to push them along. In our homes, we usually use copper, but not always. And if you're going to have conductors, it's very important that you also have insulators. Otherwise, when you touch a bare wire that's a conducting wire, then those electrons are going to travel to you, and you're going to get shocked very, very badly. That's why if you look at most wires, they have like a plastic coating around them, because plastic and that material that's made of, it's an insulator. It's made of material where the electrons are just stuck to the nucleus of the atoms and they can't flow or move at all. And so insulators protect us from conductors when there is a flow of electrons in the circuit. Now, those are the two things you absolutely have to have a circuit. You need an energy supply to push. You need a source of voltage. And then you need a closed conducting path that the electrons can move through. But there's not really any point of having a circuit unless your circuit does something. And that's where we get to number 3. Circuits have what we call loads. A load is any object or device that uses the power, the charge that's flowing through the circuit in some way. This is going to be something like a light bulb, a refrigerator, a resistor, a motor. Loads are objects that take the electrical energy in the circuit and convert it into things like heat and light and motion. So to have a full, a circuit that works, you're going to need an energy supply, a closed conducting path, and a load. And that was my dog, if you heard that really nasty sound. Now, for this slide and for the next 3 slides, I'm going to ask you to do something different. For each of these slides, there is an activity slide in Nearpod. So I want you to kind of get onto the slide and immediately stop the video. And then you're going to switch over to Nearpod and you're going to do whatever activity I've asked you to do that goes with this slide in the video. And that may be a drawing, it may be an explanation of sorts about whether you think something would work or doesn't work. I don't need you to give me the right answer, okay? I just want you to think, and I want to know how you're seeing things and what you're thinking. I don't ever want you to be afraid of being wrong. It's okay to be wrong. I'm wrong all the time. And I just want this to be a chance for you to show me kind of just like how you see stuff and what you know already about circuits. And if you don't know anything at all, that's totally okay. Just go ahead and do your best and tell me what's in your mind when you look at that slide and respond to that question. Okay, so for each one of this slide and the next 3 slides, you're going to get to the slide and then you're going to turn the video off, go to Nearpod, answer the question there, submit your answer, and then come back and turn the video on and listen through. And as soon as it switches to the next slide, pause the video again, okay? And I look forward to hearing from you. So the time to pause the video is right now for this slide. So if you look at this, you might think that, oh, well, maybe that would work. After all, here we have a battery, that's a power source. We have a positive side to the battery and a negative side to the battery. And we also have a load, this is our light bulb here. And we have a wire, a conducting pathway. But if we could be in the classroom and try this, we would discover that this does not work at all. Why would that be? Let's keep on moving. Interesting. Okay, so what about this one? What did you think? Now here we have that positive side of the battery and the negative side of the battery. Here is our load, our light bulb. We have the wire touching the metal, conducting, maybe, and then we have it touching here. But notice how both of the wires, this one is touching the positive side of our power source, and then it's just touching, you know, the light bulb. And then look here, we're touching here too. So the light bulb is actually touching the positive side of the battery twice, but nothing's touching the negative side of the battery. So am I really making a complete loop through the power source? I don't think so. I don't think this one would light up if we could try it in the lab. Okay, what about this third one? Here's our positive side of the battery, negative side of the battery. I have metal and metal touching, so that's both conductors. So I should be able to have current come out. Then it would go through the wire. It would come back in the negative side. And boy, that kind of looks like that's a closed loop now, doesn't it? If we could do this in the lab, guess what? That light bulb would light right up. So what is a circuit? A circuit is a pathway that allows current or charge to flow through it. And in order for that current to charge or charge to flow, we have to have a conducting pathway. And that pathway has to be closed. That means you have to be able to go from the positive side the whole way around to the negative side of the power source and come right back in. All right, so we've used the word current, and all we mean by current is just that flow of charged particles through the conductor. In the case of a wire circuit, it's just the electrons that are flowing or moving through that wire. And if I could stand at one point and just look at the wire and kind of count how many electrons were bouncing past at any given moment in time, I would be measuring the current. Now, our unit for that is going to be something called a coulomb per second. And coulomb is simply a measure of charge. Remember, all those little electrons are carrying tiny negative charges. And that adds up when you have a lot of electrons moving or flowing through the wire. And so we measure in coulombs per second, but we also call this unit an ampere, or an amp for short. And we use the unit symbol capital A. Now, 1 amp of current means that if I'm standing there looking at the wire, 6 times 10 to the 18th electrons are going to pass me by every second. That is a lot of electrons. Okay, remember, we're talking, even in a thin wire, about atoms, which are very, very tiny, and there are tons of atoms in every little tiny object. And the electrons, they're even tinier than the atoms are. And so we're talking about very small negatively charged particles flowing or moving, and we're talking about a lot of them moving every second. Now, when we have talked about current in the past in physics, there have kind of evolved 2 different ways of describing current. We're going to use the one that is called conventional current. In conventional current, we kind of think about the flow of positive charge. Now, this isn't quite right because remember, it's not the protons that are moving, it's the electrons. What's actually flowing are the electrons, but we think of it this way for reasons as a flow of positive charge so that the current flows away from the positive side or terminal of a battery, let's say, through the conducting pathway of the wire and back toward and into the negative side of the battery. This is what we are going to call current, and we're going to use the symbol I. Now, electron current is the more proper way. If you could actually get inside the wire and look at what's happening, you would see the little electrons flowing, but they would be flowing in the exact opposite direction of the conventional current, the way we say it, which is unfortunate because it would be nice if we just had one way of talking about it. That's why we're not going to talk about electron current. We are going to talk about conventional current. I just want you to be aware of electron current, especially if you get into engineering and stuff like that, or further on into physics, you will switch over in many cases to using electron current. For us, we're going to use conventional current, and this is the big thing to remember. Current flows away from the positive toward the negative. If you're having trouble visualizing this, sometimes it helps to think of current in terms of water, which is a lot more familiar to us. You know that you can turn on your water faucet at home so that it just trickles, or you can turn it on the whole way so that lots of water comes out. And it's very similar in circuits with electrons. High current in water means lots of water is flowing. It means that there's a lot of water coming out of your spigot, and everything gets all wet. And low current in water, that's that little bit of trickle where there's hardly any water, it's just kind of dripping out. In electronics, it's the same way, except that the current is the flow of charge. It's the flow of the electrons, not water. And so we have a lot of electrons moving through a wire if there's high current, and we have not as many electrons, a much smaller number of electrons moving through the wire at any given moment in time if it's a small current. Remember, it's electrons that are doing the moving or the flowing, and this is why we call all those great things like our video game console and our cell phones and these computers that we're working on. That's why we call them electronics, because they're all made possible by this flow of electrons through a closed circuit. Now, one of the fundamental features of circuits is something called resistance. And resistance is kind of the hindrance to the flow of charge through a circuit. I mean, electrons would like to move through a circuit basically at something close to the speed of light. But any electron moving through, let's say, a copper wire, it's going to keep bouncing into atoms of copper. And so it can't just go, in a straight line as fast as it wants to. Think about it this way. If we were back in school and you're in a hallway in, let's say, the 800 building, and, would it be easier and faster for you to run down that hall, one of the hallways in the 800 building at top speed, if there were 10 people in the hallway or if there were 100 people in the hallway? With 10 people, you could take a pretty straight path and you could probably avoid them. But if there's 100, man, you're going to be knocking into people. They're going to slow you down. They're going to resist your ability to make that straight line run through the hallway. And the very same thing happens inside a wire in a circuit. All the atoms of copper, let's say, and all the other electrons and everything else is kind of jammed in there. And as the electrons are trying to move, they're bouncing and smacking into other atoms and molecules, and it slows them down. Now, we call this natural resistance in a wire, or we call intentional resistance that we add to circuits. We call them both resistance, and we use the unit of the ohm, O-H-M, ohm. There's this funny cartoon in the bottom right, the ohm. This is one of our favorite physics cartoons. You will see it everywhere. And that thing that all the monks are sitting in front of is what a resistor looks like, your typical resistor in electronics. And so our symbol for the ohm is that funny little kind of squiggly symbol on your screen. This is actually the Greek letter omega. It is the final last letter of the Greek alphabet, and you can practice drawing that because you are going to need to use that here by the end of the week. So just practice drawing that a little bit. Resistance is this hindrance to the motion, the flow of the electrons through the circuit. And like we said, the resistance comes from the nature of the material in the circuit itself. It comes from the conducting material, the copper, let's say, in a wire. And all kinds of different things will affect how much resistance the electrons experience just because of what they have to move through. What it's made of, what the wire is made of. The resistance in aluminum, for example, is going to be different than the resistance in copper, just based on how aluminum atoms pack together and move. And it depends on how long the wire is, It's a lot different to run down a hallway that's, let's say, a quarter-mile long filled with people than it is to kind of like rush through one line of people and into the end zone, let's say, if you're playing football. So if the longer the wire is, the more resistance, because the more time, it takes longer to get through it and you're constantly experiencing it. And also how wide the wire is. There's all kinds of things that affect how much resistance that the actual material of the conductor itself provides. This is why, I don't know if you've noticed this, but sometimes wires and stuff will get warm or hot when they are conducting electricity, when they have a flow of electrons in them. And that's because every time those electrons smack into a molecule or another atom, that releases a little bit of energy as heat. And so you get all those electrons going, you get a lot of heat that's released. So we need to protect sometimes the materials around our circuits from the heat that's generated by the electrons moving through our circuits. And then other objects in the circuit, everything from your light bulbs to your resistors, which are specially designed to offer a certain amount of resistance, to your refrigerators, to your microwave, everything will add resistance to the circuit. We're going to talk later on this week about how to figure out how much resistance there is in a circuit, how to calculate it for different circuits. But in the meantime, join the resistance. Now, when we want to draw a circuit so that we can analyze it and see how it works, we do that using a special kind of diagram called a circuit diagram. We pretend that we're building the circuit like on a tabletop, and then we're looking down at the actual circuit as it's constructed. And we use a whole bunch of special symbols to represent the different components or parts or objects that are present in our circuit. A couple of common ones are right on this page here. If you can see, I'm not sure if my cursor will actually show here, but we have a battery or power source which has a positive side and a negative side. We have a bulb, like a light bulb or a component. There are a couple of different symbols. That's one of them, that kind of loopy circle thing. And then the wires or the conducting pathway we represent with lines, just straight lines. And in a closed circuit, current flows around the loop from the positive side back toward the negative side. So you can see in this circuit that's drawn on the computer screen here that current is going clockwise. It's coming out of the longer side of the power source that has the plus, and it's moving around it, and it's coming back in the negative side. Remember, electrons are going the other direction, but the way we're going to think about it, it's going to be clockwise. Now, if you look here at the little GIF on the, and don't argue with me over GIF or GIF, please, on the light bulb, you'll notice that when that wire gets to the light bulb, basically the electrons are routed up through a wire in the light bulb, and it loops through and through a filament, a very super thin part, and then comes back down. We will actually talk about how a light bulb works. This is a special light bulb called an incandescent light bulb. This is not an LED or a halogen light bulb or something like that, or a fluorescent. This is an incandescent light bulb. And the current flowing through the filament makes it glow. It takes some of that electrical energy of the electrons moving and converts that into light, and in the case of an incandescent, into a lot of heat too. They get very, very hot. If there is no loop, no closed circuit, there is no current, and then there is no light. Now, we're almost done, I promise. We have three types of basic circuits that we're going to learn about in this class. The first kind is called a series circuit, and this is where the circuit is just one loop and the current has to pass through every object on that loop, and there's only one path for the electrons to take. They can only go one way. And if you break that wire or you break that current, that circuit, that pathway, anywhere, the whole thing goes dead, okay? This is like the old style Christmas lights. I don't know if you've ever had old style Christmas lights where you know, if one bulb blows out, the whole string of Christmas lights goes dark. And then when I was a kid, I would have to sit on the floor of our house and I would have to take a brand new little tiny light bulb and I would have to stick it into each of the light bulb sockets on that string until I got to the one that made them all light up again. Series circuits are simple, but kind of annoying if you're the person who has to sit on the floor plugging in a tiny little light bulb to 100 little light bulb sockets trying to make it work. That's why parallel circuits were developed. Parallel circuits are better in some ways because there's more than one pathway that the electrons can take. For example, let's say that we have current here in our example circuit under number 2, parallel circuit. The electrons can either go through that A loop or through the B loop or through both loops at once. And so if A breaks, let's say that light bulb on A breaks, well then the electrons can still go through B. This is how new Christmas lights are. if you've ever noticed with new Christmas lights, and by new I mean since like 1985, I shouldn't say new, with modern Christmas light strands, there are several circuits, parallel circuits, all in one strand. And so if a light burns out, maybe only every third or fourth light bulb will burn out because there are other pathways that it can take through there. And so it's not as catastrophic as if half your Christmas tree goes dead because, you know, your series circuit light bulbs that you got on the cheap, you know, were really not so great. These are the two main types, series circuits or parallel circuits. But you can also have a combination circuit. This is kind of like a series circuit with a parallel circuit built into it. And we'll talk more about those later. But you are going to practice, your next activity in class is going to be practicing creating some circuits. And so you should study these carefully. Series circuits, parallel circuits, and combination circuits. I will put this entire PowerPoint that this Nearpod was built off of, I'll put this all in your OneNote, your notebook, so that you have access to all these drawings and diagrams. And finally, the very last slide. I know you can't wait. So here are just a few of the electrical circuit symbols. This doesn't include all of them. There are so many. And it doesn't include some of the good ones. Like, it's hard to find the perfect symbol graphic. So you can always, if you are having trouble remembering, you can always just Google electrical circuit symbols and you're going to come up with a bunch. You can use them, okay? There is a little bit of difference sometimes in terms of which symbols are used in the United States versus symbols that are used in other parts of the world. But for the most part, I'm going to be able to read what you do. I'm pretty fluent. So some of the symbols that we're going to use all the time, power source, down on the bottom row, third one in. We're going to use that one in every circuit that we do. We're going to use light bulbs right above it. And there are different symbols for different kinds of light bulbs, LED lamps, so you can see neon lamp there, regular. I actually tend to use that X one with the circle. That tends to be the one that I use, but you can use any one that you want. And that loopy one that's on our other diagrams, that's another one that you can use for light bulbs, or what we call lamps. And resistors. Resistors like the lightning kind of zigzaggy symbol that we use here in the US for it. And, you know, there may be some other ones that we use further down the line, but those will get you a long way. Now, there's also a switch. A switch is simply, you know, it opens up the circuit and then it closes down the circuit, opens, closes, opens, closes. We will be using, and you'll be seeing some switch ones too. And you have survived your first PowerPoint in physics. Congratulations. And finally, the very last slide. I know you can't wait. So here are just a few of the electrical circuit symbols. This doesn't include all of them. There are so many. And it doesn't include some of the good ones. Like, it's hard to find the perfect symbol graphic. So you can always, if you are having trouble remembering, you can always just Google electrical circuit symbols and you're going to come up with a bunch. You can use them, okay? There is a little bit of difference sometimes in terms of which symbols are used in the United States versus symbols that are used in other parts of the world. But for the most part, I'm going to be able to read what you do. I'm pretty fluent. So some of the symbols that we're going to use all the time, power source, down on the bottom row, third one in. We're going to use that one in every circuit that we do. We're going to use light bulbs right above it. And there are different symbols for different kinds of light bulbs, LED lamps, so you can see neon lamp there, regular. I actually tend to use that X one with the circle. That tends to be the one that I use, but you can use any one that you want. And that loopy one that's on our other diagrams, that's another one that you can use for light bulbs, or what we call lamps. And resistors. Resistors like the lightning kind of zigzaggy symbol that we use here in the US for it. And, you know, there may be some other ones that we use further down the line, but those will get you a long way. Now there's also a switch. A switch is simply, you know, it opens up the circuit and then it closes down the circuit, opens, closes, opens, closes. We will be using, and you'll be seeing some switch ones too. And you have survived your first PowerPoint in physics. Congratulations.